So in this next example, we're going to look at throwing objects into the air vertically. And so you have this initial force. It might be your arm. It might be some kind of launcher. If you're launching an arrow, it would be your bow. But something is launching something into the air. Maybe we're just dropping it. That could work as well. But I want you to realize that when you let go of the object, as soon as it leaves its launcher, whatever that might be, then there's no more acceleration given to it by an outside force other than gravity. So the only thing that's accelerating your object is gravity, and it's constant. So it's pulling your object, it's tugging on your object, it's accelerating it at a rate of 32 feet per second, and that's just a constant rate of gravity, and you'll want to be aware of that number. It pops up. This is an approximation. It's not precise, but it's close enough for engineers. So I wanted to do an example with you. You can imagine this being the cliff, the point here at C of O. However, I have to warn you, throwing rocks off of cliffs onto rivers below could be very harmful to people who are fishing or swimming or hiking. So perhaps as a caveat, you should not actually do this in practice, just so that nobody can blame my videos for getting bombarded with rocks. Actually, there are some places like canyons and things I've hiked in where there are very clear signs, do not throw rocks off the edge of cliffs because you could kill somebody below. And it's true. But anyway, we're going to talk about throwing rocks off of a cliff only in a theoretical sense. We're never going to go do this so that no one will be hurt. So a rock is going to be thrown upward at a speed of 48 feet a second from the edge of a 432-foot cliff above a river. And yes, if you were standing here, then technically the rock is starting wherever your arm height is. We're going to imagine the rock starting sitting on the ground. Somehow you lay down and fling it straight up so that it's starting exactly right here. It goes up, then it's going to fall down. The way I've drawn it, it's not actually in a line. The way I've drawn it, it's going to go out and then down. We need to actually assume straight up and then straight down for this model to work, but you can imagine holding it over and flinging it. Anyway, so the cliff is 432 feet. Here's the river up and then down. We're going to wait for that lovely kasploosh, which we'll never hear in real life because we won't throw rocks in cliffs because we don't want to kill anyone. Anyway, all right, so let's see if we can figure out what they're asking for. So they first want, they being me, I guess, I'd like a formula for the height of the rock after t seconds. And so this is just going to be S of t. I'm just looking for S of t. Then I have two other interesting questions. So when does the rock reach its maximum height? I didn't actually ask for what the maximum height was. You could figure that out if you wanted to, but I just asked, when does it happen? Make sure that we answer the question. And then when does the rock hit the water? And so let's work through this together. And you should be, after this video, you should be in good shape for the homework. So let's realize that once we let go of the rock, the only force acting on it is acceleration. And so I should caveat, I'm not a physicist. So a physicist might listen to this and disagree with me. But in my perspective, the only force acting on this rock is gravity. And so we're going to start out with my acceleration is going to be negative 32. I'm constantly accelerating downward at 32 feet per second. Even though the rock is actually going upward, it's accelerating in the negative sense due to gravity. It's slowing, and now it's going faster down like that. Okay, so acceleration is minus 32 feet a second. It's constant. That means I can immediately figure out what the velocity is because I know that v prime is a. So v of t is going to be negative 32t plus a constant c. Now I've got to figure out what c is, but we realize that, wait a minute, I know what the velocity is at time 0. This thing was launched at 48 feet a second. So I know that v of 0 is, on the one hand, it's c, and on the other hand, it's 48. And so we know that c is 48. So that tells me that the velocity function is minus 32t plus 48. That's really nice to know. And now I can figure out what my position function is. So S of t is going to be negative 32t squared over 2, taking antiderivatives, plus 48t plus another constant, let's call it d. And then we need to figure out what d is. Well, what's s of 0? I wasn't sort of told that, and yet I was. S of 0 is the height of the rock at time 0. Well, you're sitting right at the height of the cliff, so S of 0 for us is going to be 432. Well, when you plug in 0, 0, 0, you get out d, so that means that d is 432. So I can actually write down S of t in full generality. I get negative 16t squared plus 48t plus 432. And some of you are looking at this wondering if it generalizes, like, does this always work? And the answer is yes. When you're throwing things up in the air, it's always going to be negative 16t squared. That's your gravity. And then this number here is the initial velocity, and this number is your initial height, always. But we just sort of discovered that on our own from the ground up. Okay, so that's actually the first part of the question. I was asked to find a formula that gives me, whoa, the height of this thing after time t. That's cool. And we did that. Maybe we should actually label this. This is the height after time t. So now I'd like to answer the other two questions. So let's think together. When do I hit maximum height? I hit maximum height. Well, you could approach this from a curve sketching technique. Maximum height, I'm looking for the absolute max. It's going to be a local max because this is a quadratic opening down. So maximum height is just going to be at the vertex of this quadratic. That's one way you could do it. Or you could say, well, gee, when I'm at the maximum height, that means the rock is actually stopping for just a moment. Its velocity is 0. Its velocity was positive, and all of a sudden it's going to be moving in the negative direction. So maximum height happens. That's how I'm going to approach it, is max height happens when the velocity is 0, i.e., I want to solve v of t equals, well, we said negative 32t plus 48, and I want this equal to 0. So I get t equals 48 over 32, which is just 3/2. So we now know that max height is reached after 1 1/2 seconds. Okay? I didn't tell you what it was. If I wanted to tell you what it was, how would we do that? Pause the video and think about that. Well, you would just compute S of 1.5. That's equal to the max height. I'm not going to compute it because I don't care. Now, I want to know, when does the rock hit the water? Well, the rock hits the water when its height or its position equals 0. So we're just looking for, when does S of t equal 0? And so I have, just going to write down my equation for S of t. So I get negative 16, can't quite see it on the screen, negative 16t squared plus 48t plus 432 is 0. You can factor out a 16 and actually cancel it, and a negative as well. So I'm going to get t squared minus 3t minus 27 is 0. Doesn't factor, so I'll use the quadratic equation, and I get t is 3 plus or minus 3 root 13 over 2. The negative root is, so our rock is starting here and going down. The negative root is going negative time, actually. We don't want negative time, so we're going to take the positive root, and we're going to get 3 plus root 3 over 2. This is roughly 6.9 seconds. So let's finish with a sentence so that it's clear. So the rock hits the water after 6.9 seconds of flight. That would be an awesome experience, to fly in the air like that for 6.9 seconds. All right, you've got everything you need to do homework number 20. Let me scroll up here. Homework number 23. And that is the end of chapter 4. Way to go. I'll be in touch soon regarding what's next. So hang tight, and you can, in the meantime, work on homework.